This is chemical state analysis by XPS, and what we'll do is look at some issues that may be found when you're analysing data from different samples when measured by XPS. Now, the first thing you typically do is look at a survey spectrum, and in this case we're looking at a sample we believe to be polylactide, and the polylactide ought to give us oxygen and carbon in a given ratio, and it should be 3:2, and when we look at the survey spectrum, indeed we get 3:2, so we have evidence now that supports the assignment of polylactide. However, this is not really enough. We need to consider a little bit more than simply the survey spectrum for the following reasons. This is an example of copper nanoparticles supported on graphite, and this survey spectrum, when you look at the copper to the oxygen, it suggests that you've got roughly 1:1, slightly more copper than the oxygen, but about 1:1, so you might suspect that you've got something that is predominantly CuO. However, when you look at the high resolution spectrum and you do a peak model based on using copper 1+, copper 2+ oxide and copper hydroxide, you can see that the peak model is suggesting that we've got roughly equal amounts of hydroxide and 1+ copper oxide, and the composition of these are 2 copper to 1 oxygen in one case and 1 copper to 2 oxygen in the other case. Therefore, the composition as measured by the survey spectrum should be about 1:1, which is exactly what we're seeing. So the survey is not giving us the full story, and we must do a peak model. So going back to the polymer, if we look at this again in terms of the high resolution spectra, we've got a little bit more evidence. We've got oxygen, 2 peaks of oxygen to 3 peaks of carbon, and the amount of carbon and the amount of oxygen, the shifts in the energy, they're all supporting the idea that what we have are a single bond and a double bond of copper and oxygen, which is what we see in the expected structure for this polylactide. And so we feel much more confident now that we actually have a polylactide. But if you really want to feel confident, you should look at a database, and in this case we've got a well characterized polymer database by Beamson and Briggs, and if we look at their data, we can see that we have a very, very similar peak structure and organization to the Beamson and Briggs. So this is probably polylactide. Now, another issue that can occur when trying to look at a proportion of oxygen to carbon or any other materials is if the sample is not homogeneous over the area analyzed, and it can easily happen. And this is an extreme case where the sample is designed to be inhomogeneous, and you can see how if you choose different squares to sum the information to obtain your spectra, you can get quite a range of different compositions of chromium to indium, say. And this actually appears in normal samples. This is representative of a molybdenum oxide sample that has been prepared using electrochemistry, and you do not get a delightfully uniform surface to analyze, and the result is that you get variation as a function of where you analyze and the size over which you analyze. So you can see here 4 examples, and you've got 2 of them are measured with good precision, 2 are not so good precision, but nevertheless the uncertainty is not sufficient to account for the differences throughout these different measurements, and one in particular is really quite bad. It's offering about 89% molybdenum and sulfur 2s signal compared to the sulfur 2p. You may have a uniform surface to analyze, but you may not have a uniform depth to analyze, and the depth distribution, when it varies, can produce quite interesting results in XPS. And the reason for this is that XPS is surface sensitive, and using an exponential attenuation model for XPS data, where the electrons are attenuated by the material above them after excitation. 95% of the signal originates from the top 3 attenuation lengths in depth. 63% originates from the top third. So that means that a material at the surface will be favoured by XPS over a material that is beneath. If it's at a depth of 2 attenuation lengths, then you only get 8.5% from a third of the surface, which is not entirely bad, because this is one of the properties of XPS, is that you can get more than one spectrum from a sample by performing experiments at different angles for the sample. And here we have an example of a polymer, which is polyvinyl ethyl ether on top of a polystyrene, and if measured with a normal at 90 degrees, you can see the polystyrene peak in the data, carbon 1s, whereas if you tilt so that instead of 90 you have 10 degrees, you cease to see the polystyrene clearly. It's there, a small amount, but it's not as well defined as you might expect given the sample composition, and this is a consequence of tilting the sample. So if we look at a sample that has been analysed at 90 degrees, and then we do a peak model, and then we do a survey spectrum and calculate the proportions of oxygen to carbon, we know that the polyvinyl ethyl ether ought to have a ratio of 4 carbon to 1 oxygen, whereas the polystyrene is entirely made up of carbon with the exception of hydrogen, which we can't measure. So if we do a survey measurement and take a high resolution spectrum with the peak model, we need both of these together to actually understand that we have got a polyvinyl ethyl ether, because when we look at the oxygen and the carbon from the PVEE, you can see that there is 4 times the carbon compared to the oxygen. So it requires more than the survey spectrum to perform this type of assignment in terms of chemical state.